first. So this is an MCQ. Now, this question says that a gas molecule of mass m is traveling at a speed of v and strikes the side of a gas cylinder at an angle theta, and the collision takes time t seconds over here. Like the total time for the for the time duration for which the gas molecule was in contact with this what is this glass cylinder was t time. Okay, and now it is stated that what is the average force acting on the side of the gas cylinder, not on the gas molecules, just specifically focused on the gas cylinder. Okay, now over here, I'll obviously distribute the forces first. This is a vertical plane and this is my horizontal plane. One thing wrong about this initial velocity is it was moving towards the center, right? Whenever I'm going to distribute it, it must move away from the center. In that case, I cannot distribute it in these two planes. I need to move it to the other section, other quadrant, and then distribute it in between the positive y-axis and positive x-axis, right? Because according to the previous sections, we understood that any kind of vector quantities, we cannot distribute them if they are traveling towards the center of the origin. So in this situation, again, I'll have to extend this. Okay. They both have the same magnitudes. This was, by the way, for initial velocity. Okay, and this is, by the way, your final velocity. Final. Okay, and I can clearly understand. In this case, your final velocity will create a component that is going to be v cos theta, right? And then your horizontal component will also be v sine theta. Let's just use a different ink for the initial component. For initial component, again, it was creating what? As it was creating theta degree with the vertical, in the other plane also, when you're going to extend this to the other quadrant, it will also create the same angle with the same plane, with the vertical plane. And then again, if this was also v, it will have the v cos theta in the vertical plane as well. So v cos theta, and on the horizontal plane again, you will have the v sine theta. Right? This is how we'll distribute the diagrams. Now, after this, I can understand that this was actually your initial velocities component and this was actually your final velocity, right? So I can understand that, let's use another different name. This is u. U is actually v sine theta, and this is v, which is also v sine theta. And in this situation, these values, V cos theta will not be required because we're only focused on to find out the forces acting on the two particles, right? So the forces are going to be exerted on the two particles in between the horizontal plane, not in between the vertical plane. So nothing will be added or nothing we can get from the vertical planes over here. So we're not going to get focused on the vertical plane. We're only going to focus on the horizontal planes over here. Another thing, if I draw a very small diagram about the same thing, which is occurring over here, this was your gas particles and this was your object. So this was a gas particle and that was the wall. When they are colliding with each other, obviously there's a force in this direction. This is the force on the gas cylinder. And again, in the opposite direction, there will be a force on the gas particle. Right? They will be obviously in opposite directions with the same magnitude. On gas molecule. Now, from this diagram, I can understand that your force on the gas cylinder was acting towards right, and force on gas molecule was acting towards left, right? Now, in this situation, all the information that have been provided in your question was all regarding the forces or all regarding the velocities in terms of the gas molecule. There was no information that was provided for the gas cylinder. Everything was provided in terms of the gas cylinder, in terms of the gas molecule. So what you have to do, you have to calculate this entire thing in terms of the gas molecule and then reverse the direction. Okay. So in this situation, if I start working with, for example, let's start working with this let's just understand that why this vertical component will not give you anything. Okay, I mean, in this situation again, I have to use your I think it was derivation 2. I'm not quite sure. It was this one, impulse force time, and the other equation was impulse mv minus mu. So what I can do is that I can substitute the first equation into the second equation to get ft mv minus mu, and to calculate force I'll have to use the equation mv minus mu divided by time. Okay. Now in this situation, if you remember, this was for the vertical plane. This is your initial velocity. This is for your final velocity, right? Now, if you want to find out that what is exactly the force exerted on the particle in the vertical plane, and they were all traveling in the same direction, right? That means both initial and final is positive. No one is negative for the vertical plane because they are both traveling in the upward direction. They're both traveling in the upward direction. So initial velocity and final velocity, they are both going to be considered as positive as they are both traveling in the same direction. So if you start resolving vertically, even though we do not need this, I'm just explaining this that why exactly this gets cancelled out over time. So I'll just work with a very derived format, right? I've already derived the formula mv minus mu divided by t. Whatever the mass of the particle is, I'll just consider the mass is still as m. So this is going to be m v cos theta minus mv cos theta. This time, as none of these are moving in the opposite directions, they will never get added together, right? They will easily cancel each other out because they are both positive. That means the minus sign in between the equation will get restored, and mv cos theta will be cancelled out with the mv cos theta divided by 0. So what do you have at the end? You have F equals to 0 over T, and eventually the force is 0. That means in the vertical plane, no force was exerted onto the gas molecule or onto the gas cylinder. Is there any question explaining this part?
No questions.
No, miss.
Okay, then we'll move on to the main concept, that is your horizontal axis. Now in horizontal axis, I can understand that this is in the opposite direction, maybe towards the center, like towards the left, so right direction, and this is in the left direction, right? Exactly which particular direction will be considered as positive and negative, that is not a matter for me. As I want to find out the cylinder, I mean the force exerted onto the cylinder, and the force exerted onto the gas cylinder was actually towards the right, right? So I'm going to consider the right direction as positive because that's what I want to find out. So I'll consider that as positive and that as negative. Also, there's also one hint in your question. All the possible answers are positive, right? And over here, we're only focusing on the force exerted on the gas cylinder. That means in this particular max, they're considering the right side as positive, not the left side. And that's why all the possible answers are actually given in terms of positive direction or in terms of the right, considering right as positive, right? That's why I'm also taking that as a hint from the all the options, and I'm taking the right direction as positive. So now we're going to calculate that exactly how to find out the force in on the gas molecule. By the way, the thing I'm going to calculate is for the gas molecule, not for that. What is this? Not for the gas cylinder. Okay. So for that gas molecule, this is positive and this is negative. So which turns out to be this is F mv minus mu over time, and this is going to be, as v is negative, it will be negative mv sine theta, and then again mv sine theta divided by mv sine theta divided by t, and it will be eventually minus 2 mv sine theta divided by t. But you are getting this minus sign. Why? Because this was the force exerted onto the gas molecule, and it was actually exerted in the right left direction, right? And according to your assumption, you consider the left to be negative. So this is correct. But if you want to find out the force exerted on the gas cylinder, it will have the same magnitude, but not the negative sign, because it was now exerted on the gas cylinder in the positive direction. So in that sense, option D is your correct answer. And all this working just for 1 mark. I mean, obviously, with practice, you guys will not need to think so much about this angular momentum, but as this is the start, this is how you should approach any question for angular momentum. I mean, with few practices, I think you can also calculate this final answer even without any kind of calculations required. You will eventually understand the answer. They have the similar kind of pattern, but so far, this is how the introduction looks like. Is there any question? Please go through this entire part and let me know if there is any problem.
No questions, Miss.
Okay, I'll just wait for a few minutes for others to see the question and then we'll move on.
Miss,
Yes, Hamza?
Miss, I have a question that, like, at the end, you went for the final velocity. The equation is mv minus mu. Then why did you like go for the final velocity for both the cases?
Oh, because the object was traveling with same speed. Right, over here, if you remember, mass m traveling at speed v strikes the side of the gas cylinder, right? It never changes the velocity. As you can see, the original diagram, it was moving with the initial velocity was also v and final velocity was also v. That's why v and remain same. They have the same magnitude, only different directions.
Okay, Miss. Thank you.
Okay, I hope that is it. This was the done for one MCQ. Let's move on to the next MCQ. We'll obviously solve theoretical questions again, but let's first solve the MCQs first. Okay. Now this is again another MCQ from June 21. Again, this is not your final worksheet. Okay, this is just a worksheet that I made in order to solve your in order to get a concept about this angular momentum. This is not a worksheet that you guys are going to solve. Okay, now again over here it says a sphere traveling at speed v collides elastically. Always remember, in order to follow the law of conservation of momentum, every collision has to be elastic, right? In the previous example, with that gas molecule with the gas cylinder, that was also a situation for elastic collisions, and this is also a situation for elastic collision. Right? And it is already stated boldly in the question that over here the object is traveling with elastic collisions, right? And with an identical sphere means they both have the same mass, whereas this second sphere was stationary and the first sphere was moving towards the stationary sphere with a speed of v meters per second. And after the collision, both spheres move off at an angle of theta degree to the direction of travel. Direction of travel means that previously object 1 was traveling in the horizontal plane, and after collision, they are both going to move away from each other with respect to the horizontal plane, right? So this is the horizontal plane, and this is their angle, corresponding angle that they're creating with respect to the horizontal plane. If I would have to, maybe draw a very simple force diagram, free body force diagram, this is how it will actually look. Right, this is maybe your object A, this is maybe your object B, and then again this is A and B, and as they move away from each other, according to the horizontal plane with theta degree to the horizontal plane, right? That is how it was actually occurring. And again, after this, it stated that the spheres have the same speed as each other. That means again, after collision, they would have the same speed. Okay, as they have already used v for the initial velocity, so I cannot use u. Let's just use s for the final velocity. Okay, so I'm going to consider this as s and this as s. Similar concept, I will have to distribute the after collision situations because before collision it doesn't have any hassles. After collision, you have to create the components. So now it will have this s cos theta. So s cos theta. And in the vertical plane again, you have s sine theta. Now I'm going to find out the speed of the spheres after the collision. So in this situation, I can understand that if we focus on the vertical plane, only after collision the particles have a vertical motion, right? Before collision, the particles did not have any vertical motion. As you can see, there was nothing over here in the vertical plane before collision. So but before collision, there was nothing. So I can consider that even if I start using the vertical motion, okay, even though that is not required, but still let's just work with that. Also, in this situation, they're asking you about the speed, not about the velocities. Speed indicates that they basically want to do this maths entirely in terms of kinetic energies and not in terms of your what is this in terms of momentum concept. I mean, you can also solve this in terms of moment concept, and that will eventually give you the same answer. But working with energies theory is much more easier, but because it was also stated over here that was all elastic collision. That means before kinetic energy, after kinetic energy was conserved. So it will be easier to work with kinetic energy. Then you should, and then that uh, momentum, conservation of law of momentum. Now, if we start with this vertical plane, I can understand that for the vertical plane, this will get cancelled out with this way, this one, and the final velocity will eventually be zero because the particle before collision does not have any velocities in the vertical plane. So if we start with the vertical plane, we'll write kinetic energy before collision is equals to kinetic energy after collision, and that will be equals to before collision. After collision, you have half m 0, right? Because in the vertical plane, before collision, there was nothing there. And this is equals to half m, that s sine theta square plus half m s sine theta square. So eventually what? You're going to get all of these things that basically m s sine theta whole square equals to 0, right? Anything to the power of 0 will give you 0. So that at the end, your speed turns out to be 0, so which is obviously not correct. So we're not going to use that. Another thing to understand, for this specific mass, no need to actually like distribute the components as v sine theta or cos sine theta or something similar like that, as we were only focused on the speed, which is just the magnitude. The V sine theta, like sine theta, cos theta, they indicate the direction over here, like in which plane your particle have a velocity, right? That indicates the direction. Over here, I was only focused on the speed. So speed is basically a magnitude, and I'm only focused on the magnitude, not into your concepts about your directions. So now, if you want to actually do the working, which is required for this maths, which is a part for the part for the horizontal plane, I'm not going to use the displacements, sorry, the speeds as v sine theta or s sine theta or s cos theta. I'll only use their magnitudes, and their magnitude was s, and v. Okay, without the direction, this alphabets represents their magnitude, and this s sine theta, s cos theta represents the final velocity of the particles. We're not focused on the velocities. We're only trying to find out the magnitude over here because we are clearly boldly stated we want to find out the speed, not the velocity. Okay, always remember speed is the magnitude version of velocity only. So now we are going to start with kinetic energy before collision and then again kinetic energy after collision. So for this case, we are going to start with um, right half mv square. This is for the particle 1 and particle 2 was stationary, so it will have zero kinetic energy. And then again sorry, half m is square plus half m is square, right? It was also stated, 1 minute. It was also stated over here that both were identical sphere. Identical sphere means that both the spheres have the same masses and after collision, they would both travel at the same speed. So speed is same, mass is same. So eventually this turns out to be half m v square is equals to half plus half is just 1. So you get m s square. So this masses gets cancelled out and you finally have, I'll invert the equation. So you have s square v square over 2. If you take this square from the left hand side to the right hand side, it's going to be v square to everything under our root. So v square under a root turns out to be v divided by root 2. And this is exactly your option B. Okay, that is your correct answer then. So if I zoom out, this is how the entire maths looks like. Only required part was the resolving horizontal plane. And over here, for this specific mass, it was not needed specifically to distribute the velocities, right? Because in this specific mass, it was very boldly stated that, 1 minute. Yeah, it was very boldly stated that we were only finding the speed, which is only the magnitude version. For magnitude version, we also given a hint at the very top that the collision over here was elastic, right? All these were hints for you to understand that no need to work with the momentum concept. You can only use the energy conservation concept to find out the speed.
So for this question, we don't have to resolve it.
No, we do not have to resolve it.
Okay.
Is there any questions from any one of you regarding this?
No, miss.
No, teacher.
Okay. Nabila, is there any problem from your side? Okay. Then I think we can solve one theoretical question today. Okay, let's start with this one because this one is extremely big and this is actually the most toughest question momentum so far, angular momentum so far. You know, the part A is tough, part 2 is tough. Okay, now this is actually a concept from your, if you remember from IGCSE physics, there was a chapter for radioactivity, and for that specific chapter again, there was this concept for uh, photographic film that only charged particles like beta particle or alpha particles, they will leave marks onto that photographic film. Right. So over here, the similar case is that in this situation, there's a cloud chamber. We do not know yet what cloud chamber is, but we will know when we will start particle detectors. Okay. So cloud chambers are used to observe the paths for particles, and the photograph shows a pair of tracks made by alpha particles emitted by emitted when an atom of radon decays into a cloud chamber. Okay. Now, this is how the track is, right? Always remember that only this charged particle will release tracks, or will release this kind of traces, not uncharged particle will release nothing. Okay. Now, it is also stated that basically the alpha particles were emitted by the radon particle, right? But only you can see two tracks, which is for alpha 1 and alpha 2. But there was no track for the radon, right? I mean, radon nucleus was obviously there because after decay of the radon nucleus, you only got the alpha 1 and alpha 2. So why the radon does not have any trace on the photographic film? That's because radon was an uncharged atom, radon was a neutral atom, and neutral atom cannot ionize the surface of your photographic film. Only the charged particles can do that. So only alpha particles, alpha 1 and alpha 2, would leave the traces, and radon will not leave any trace or any track onto this photographic film. So now, final answer over here for 1 mark is going to be that the radon nucleus was neutral or uncharged. Okay. This is not a part of our angular momentum, but we need to solve this to solve the section C. That is actually the part of your angular momentum. But still, if there is any problem for this section, please ask now. Okay, I'm not going to bother that much for this section because cloud chambers are not a concept, but this part is extremely important. Okay, this paragraph. It says that radon decays by emitting an alpha particle. Okay, at first, radon will decay, will produce one alpha particle and also produce this polonium nucleus. The polonium then decays almost immediately. Like the polonium will not stay 1 second onto that photographic film. Right after the decay of radon, it produces polonium and alpha, and exactly at that point, polonium decays. Polonium is a very unstable nucleus. It will no longer stay there. It will like immediately decay into another alpha particle and a lead. Like the polonium further will decay into one alpha and one lead. Okay. Now this is a nuclear equation that you have to fill up. Again, I think most of you already know this is 4, this is 2, right? And this will be balanced with 2 because eventually radon divides into polonium and lead and 2 alpha, right? Because polonium again splits into alpha 2 and lead. So eventually you have 2 alpha, and then again what you have. This is basically 4 into 2, that's 8. Right, yeah. So 220 minus 8 is going to be 212. And then again, 2 into 2 is 4. So 82 plus 4 is going to be 86 over here. Okay, this is how you calculated all of these things. If there is any problem from the nuclear equation, please ask.
No problems.
Okay, so let's now move on to the next diagram. Before we move on to the next diagram, let's just read this paragraph one more time and then we'll move on to the next diagram. So at first, you have a radon particle, radon nucleus. The radon nucleus decays into one alpha and one polonium. Further, the polonium at the very instant, at the very immediate time, will further decay into another alpha and another lead. Right, that is your case. So radon directly gives alpha 1 and polonium. Polonium then decays into lead and alpha 2. So over here now it says that the radon atom was stationary before the alpha 1 emission, and the angle between the two alpha tracks is 60 degree. That was given over here in the track. Like this angle is 60 degree. I can also understand one thing is that the track for the alpha 1 is entirely vertical, right? I mean, alpha 2 is quite slanted, but alpha 1 is entirely vertical. That I can understand from this trace diagram, from this photographic film. And now we need to draw a sketch of the vector diagram to show the overall momentum of the two particles and the lead ion. There's nothing to show for the polonium nucleus. Why? Because the polonium nucleus was not actually there. The polonium nucleus broke down or decayed instantly right after it was produced. So there is nothing going to be onto the vector diagram or onto the decay diagram for polonium because polonium was kind of not there. So this is how the entire thing actually is occurring. At first, you have this radon. right? It was actually stationary. So it broke down into polonium and your alpha 1, right? Alpha 1 traveled in the vertically down direction, and then this polonium further decays into your alpha 2 and maybe in your, what was that? Lead, right? Yeah, sorry, lead. So this is for radon, this is for alpha 1, this is for alpha 2, and this one is for lead. And by the way, this was your polonium. Now, if you want to draw these things onto a vector diagram, how will you draw these things? Let's not draw this entire thing. Let's just draw a very simple, very simple force diagram, free body force diagram. But this free body force diagram has all of these things are occurring at the very one time, right? That is the breakdown for radon to produce polonium and alpha 1, and then further the breakdown of polonium into alpha 2 and lead. I can draw all of these things in one line without actually showing all the particles. This is how it would actually travel maybe. So they were creating 60-degree, and I just considered that this particle was traveling over here. Like the direction for a lead was not actually given. So I'm considering that they would move away from each other, okay, in this particular direction. So I think I should change it to over here. Okay. Now in this diagram again, if I want to create a vector diagram, this is what three different directions, right? For three different directions, I consider this as three different quantities, vector quantities. So I'll obviously use that triangle method this time. So let me just again write down the names. This is for lead, this is for alpha 2, and this is for alpha 1. This is your alpha 1 vertical. This is your alpha 2, 60-degree incline from the vertical plane. And this is your lead direction, which was over here, but I only changed the position to the very bottom. Rearranged it to make it a very closed right, not exactly right angle, triangle diagram. So this is your alpha 2, alpha 2. This is your alpha 1. And this one is your lead. Yeah, this is how the entire vector diagram would look like then. This is your final diagram. All the other diagrams that I have drawn is unworthy. That will not give you any mark. This is the final diagram. Okay, this is your vector diagram. Again, so far, this is the maximum toughest question for momentum that I have seen. In the next question, you will see that not all the questions are that much tricky like this one. Okay, is there any question still now?
No questions.
For all of you, if there is no question, then I'll move on to the next part. Then I guess there is no question. Let's move on to the next part. Yes, Saza?
Is it possible like to draw the alpha particles just in any direction as long as it's moving away?
No. No. They always have to be 60 degrees away. I mean, yeah, we can also consider writing them in this direction also. That is possible, but the angle in between them should be 60 degrees.
Okay.
And then again, this is not an accurate diagram, this is a sketch, right? So you can roughly consider that, okay, the alpha 2 can also be in this direction, but it should be like roughly 60 degrees inclined from the vertical plane. Okay, it can also be inverted. No problems with that.
Okay, thank you.
So just wait 1 minute. As I was explaining, let's move on to this third part. Now over here, this is a 6 mark calculation, so you can understand this is actually the toughest momentum, angular momentum calculation. Over here, it says that we need to find out the magnitude of the velocity of the lead ion and and the given informations are velocity for alpha is given alpha 1, which was like this is alpha 1, right? From the radon, it was actually alpha 1, and from the polonium, it was alpha 2, right? So this is alpha 1, this is alpha 2, and also the mass for lead ion is given, but the masses for the alpha is not given. Why is that? I mean, it should be given over here, right? But it is not given. Exactly for what reason? I mean, then the masses for alpha should be known to us. It should be known to us. The masses for alpha was alpha 1 and alpha 2. They will all have the same masses. That is, for one proton, the mass was 1.66 into 10 to the power of negative 27. And for alpha, if you go to the very top, you have four protons, right? Four new mass numbers. So 4 multiplied with 1.66, 10 to the power of negative 27. So that is 4, 1.66, 10 to the power of negative 27. So if we calculate all these things, can anyone please calculate this for me? What is this that we're going to get? 6.64 into 10 power minus 27. Okay, so that is the mass for your alpha particles. Okay, you have to memorize this one and then just multiply 4 with that or whatever the mass number is for that specific particle. Yes, Saza?
Do we not get the mass on the formula sheet?
Yes, it will be given in the formula sheet at the very end of your paper. And I would suggest memorize these few things. Okay, they're going to be like very few constants that you have to memorize in A2. I would suggest memorize these things. I mean, yeah, you can obviously take your answers from the very bottom of your paper, but I would still suggest memorize these values. Now, I want to find out the velocities of the lead ion, right? For that lead ion, mm, let's just use this diagram. For example, I can clearly see that alpha 2 was not entirely in the vertical plane, right? It was somewhere distorted in between the vertical plane and in between the horizontal plane. And again, for lead also, it was not entirely in the vertical plane. It was like, again distorted into vertical plane and your horizontal plane. So these blue lines over here indicates that the directions for your alpha 2 distributed in the vertical and horizontal plane, and the red line over here indicates the distribution for your lead. Okay, 1 minute, let me see. Okay, I do not have much space. Actually, I'm just going to focus on this diagram. Okay, this diagram we are focusing on. Now again, I can clearly see that basically the vertical component of lead, I do not know exactly what angle it was creating, but the vertical component of lead was equal to the alpha 1. So this was actually alpha 1. This is entirely alpha 1 and also the vertical component of alpha 2, right? It was 60 degrees over here. That means this is going to be alpha 2 cos 60. And then again, your horizontal component actually was equals to entirely equals to PB horizontal is equals to alpha 2 sine theta. Right? This is how the entire case is. So before we move on, we need to first find out the alpha 1 and alpha 2. like basically the momentum for alpha 1 and alpha 2, which is only mass times velocity. But before we move on to the calculation, is the diagram clear to all of you? Any problems so far?
No, miss.
If there is no problem, then we'll move on. Akifa, is there any question?
No questions, miss.
So now, first thing I'll calculate is alpha 1 and alpha 2. Okay, then I'll find out the components for alpha 2, horizontal component and vertical component. I actually do not have much space. So wait 1 minute. Let me just try to fit in as much as I can. Momentum for alpha 1, which is going to be, I'll not write down the formulas, okay? Because I do not have much space. So 6.64 into 10 power, 6.64 into 10 power negative 27 multiplied with 1.74 multiplied with 7. So 10 power 7. Can anyone please calculate this value for me? 1.155 10 power negative 19. Okay, that is the value then. 1.155 10 to the power of negative 19 kg meters per second. Then 6.64 10 to the power of negative 27 multiplied with 1.81 into 10 to the power of 7. That will give you what? Please calculate this again. 1.202 into 10 to the power of negative 19. Okay. So 1.202 10 power negative 19 kg meters per second. Okay, now then again, there's actually no need to calculate the vertical component of alpha 2 and horizontal component of alpha 2. Let's just find out the entire vertical component and the entire horizontal component. Okay, so for the entire vertical component, is just going to be momentum for alpha 1 and momentum for alpha 2 multiplied with cos 60 degree, right? Which is momentum for alpha 1 was your 1.155 into 10 to the power of negative 19 added with momentum for alpha 2 was 1.202 into 10 power negative 19 multiplied with cos 60 degree, right? Please recalculate this, and in the meanwhile, I think Tarushi, you missed few parts. I'll just repeat it, okay? Others, please try to calculate this in the meanwhile. Tarushi, did you saw the distributions of the diagrams over here?
Yes, teacher.
Okay. So over here, I was just trying to find out the momentum for alpha 1 that I calculated over here, which is mass times velocity. This is the momentum for alpha 1. For alpha 2, again, mass times velocity. This is the velocity for alpha 2. And this gives you again 1.202 10 to the power of negative 19. Now, I'm not going to calculate separately alpha 2 cos 60, alpha 2 sin 60. I'll consider finding out the entire vertical component because that is equivalent to the vertical component of what is this? Lead ion also, right? So I'm using that entire vertical component. I'm calculating the entire vertical component, which is basically addition of the momentum of alpha 1 with alpha 2 cos 60. So alpha 1 plus alpha 2 cos 60. Alpha 1 was this 1.155 and alpha 2 was 1.202 multiplied with cos 60. Is this clear?
Yes, please.
Okay. How much is the value? 1.756 10 to the power of negative 19. Okay. 1.756 10 power negative 19 kg meters per second. Okay. Now let's move on to the horizontal component again. That is going to be momentum alpha. I think this is only what? Momentum alpha 2 sine 60, right? Nothing else over here. So momentum alpha 2 sine 60, and this is 1.202 into 10 to the power of negative 19 sine 60 degree. Okay, please recalculate this and let me know the value over here. Okay, 1041 10 to the power of negative 90. Okay. Now, before we move on to the final step, I'll just carry all these things to the very bottom because I cannot actually write all the diagrams, all the things over here. Okay. Now, in this case, now I have the total. Yes, Saza, if you have any question, please ask.
I just want to clarify. So alpha 1, there's no component because it's acting downwards, right?
It is acting entirely in the vertical plane.
Okay, thank you.
Now, again, over here, I do not know exactly what angle lead was creating with the vertical or horizontal plane, right? And again, I do not want to know the angle because angle was only required for the direction. And in your question at the very top, it was written in bold that you only try to find out the magnitude of the lead ion, not the velocity. Like magnitude of the velocity of lead ions. Only the magnitude is required, that is the length or the size, right? Not the angle, not the direction is required over here. So if I only focus on this portion, right, now I know that your PBV is actually this one, 1.756, 1.756, 10 to the power of negative 19 kg meters per second, because momentum is conserved, right? Whatever the momentum was in the vertically downward direction, that will be same in this direction also. And then again, momentum in the horizontal direction will be this 1.041 10 power negative 19 kg meters per second, right? Is there any question understanding this?
No, miss.
Now I can use your concepts. I think these are the things we saw in projectile motion also, right? This is your vertical component, which was PBV. This is your PBA. h, and this is your actual velocity, right? This is where the object was traveling actually. I can now use Pythagoras theorem just because now I know vertical component and horizontal component are always perpendicular, right? I might not know the angle your final velocity was creating with the vertical or with the horizontal component, but I know the angle between the vertical and horizontal, which is 90 degrees. And it creates a perfect right angle triangle. So I can now apply the concepts about your Pythagoras theorem over here. So this is your final velocity. I'm trying to find out the modulus of your final velocity, right? So I'm going to write this as in terms of absolute value. And then again, this is not in terms of physics. This is for maths. You can just write velocity. That will be enough over here. So it is going to be um, PV, so PBV square plus PBH square, everything under a root, right? Which is now 1.756 10 to the power of negative 19 whole square plus 1.041 negative 19 whole square, everything under a root. Can anyone please calculate this value for me? Okay, then 2.04 into 10 to the power of negative 19 is your final answer. I will now not consider writing 2.041 because if you remember all the velocities and everything, it was given in terms of your, oh wait, another thing to actually, wait 1 minute. As it was stated that they were the momentum, right? This was actually not the velocities, these were the momentum. So for momentum, I have to use the momentum of lead also. I cannot use the just velocity. I actually made a mistake, sorry. These were momentum. That means this will only give you mv, not just v. That is where the mass for your lead plays a role. It was also given over here, right? I completely forgot about that. 3.52 into 10 to the power of negative 25 kg. 5 to 10 to negative 25 kg. Okay. Now for this situation, this is how it will be actually. Actual momentum for lead whole square is equals to momentum for that vertical component whole square plus momentum for that horizontal component whole square. I'm really sorry. I forgot that it was actually in terms of momentum, not in terms of velocities. Is there any problem so far? Is this clear at this point?
Yeah, it's clear.
Okay. So now I'm going to make this 3.52 into 10 power negative 25 multiplied with velocity, and that is now equals to your 1.756 into 10 power 756 into 10 power negative 19 whole square plus your 1.041 into 10 power negative 19 whole square. So in the next line, I'm going to get, this is also in terms of whole square by the way. Right, but I can obviously take this whole square to the right hand side and it will be eventually under our root. So eventually this is how it will look like. Okay, now if you calculate it, that will give you the final answer, the velocity of lead. And that is your correct answer also. No more mistakes. 5.8 into 10 to the power 5. Okay, and that is a value 5.8 into 10 to the power of 5 meters per second. Okay. So as I've already stated, this is the toughest maths for angular momentum. Not all kinds of angular momentum will be like this. Most of the angular momentums are easier than this. Okay, not that much tough so far. Is there any problem for this? I think this is the third question we solved. Yeah, I think this is three B2 or 3B3, whatever it is. Is there any problem so far?
No problem, miss.
No problem, miss.
Okay. Another thing I saw is that today only Akifa was there to calculate everything, and I got wait. Oh wait, sorry. Saza also said that she got, yes, that's the same value, but I mean, Akifa rounded up into that standard form. Okay. I mean, in a calculator, you might get that 5799936. That's fine. You just round this up to standard form. Okay, that is the correct answer. And then again, Saza also calculated, but for Abi, Tharushi, Sharon, and Hamza, you guys didn't calculate anything. That means in the next class, you guys have to like calculate everything we're going to do in class. Okay, and obviously you
Okay.
cannot write down the answers in comment sections. You guys have to turn on your mic and then tell me your answer.
Okay, teacher.
Okay. Miss, so when is the next class?
Our class timings are on Sunday and Tuesday, 7:30 p.m. for your time.
Okay, miss.
Okay, so our next class will be on um 25th, right? Yeah, 25th at 7:30 p.m. of your time.
Teacher,
Yes,
when is the test again?
the test will be on 3rd July.
So
3rd July,
if it's on Wednesday, what's the timing?
same class timing, 7:30 for your time.
Okay.
Okay, so this is it. Actually, there's also one more question left over here, but I'm not going to solve it in today's class. I'll solve it in the next class. Okay, so we will solve it in the next class, and this is it for today. Yes, Saza, please ask.
Will we have a class on the 1st and sorry, on the 30th of June and on the 2nd of July?
Yes, we do have classes on Sunday and Tuesday, 30th and 2nd. Will you be not be able to attend those?
No, I can attend. I was just wondering.
Okay. Yeah, we will have classes on only about angular momentum. This is from Jan 21, Unit 4. A student carried out experiments on momentum using two table hockey pucks as shown, and each contain a small fan, so they can glide across the table as a cushion of air. The mass of the pucks can be varied attaching by attaching small masses. Okay, their masses can be like changed over here. In each experiment, the student pushed one puck towards a stationary puck. That means one particle was stationary and the other particle was moving towards the stationary particle. This is entirely like scenario 2 from our theoretical classes. And again, it says that in one experiment, the first puck reached a speed of this much after being pushed for a time of this seconds. So calculate using the idea of impulse, the average force produced will accelerate the first plug, and masses are given. This is given in kg, so gram. We obviously have to convert that into kg. This is going to be what? 0.11 kg, right? And then again, now you have the mass, time, and velocity. Initially, the first particle also was at rest, right? You obviously applied some force, and after that only it was traveling, right? So, initial velocity, this is the final velocity. This is the time. Initial velocity over here for the first particle also was 0. So, in order to find out the average force that was exerted on this first particle to actually read this 0.35 meters per second speed can be calculated using this m v minus u over d. 0.11 as v was entirely, so u was entirely 0, this is going to be 0.35, 0.28. 0.35 over 0.28. 113528. And this is 0.1375. Okay, that is your 0.1375 Newton. But obviously, I cannot accept my answer in four significant figure. All the data in the question was given in two significant figure, right? So I just accept what? 0. Right, 0.14. That is acceptable. 0.14 Newton. That is the average force that was exerted onto this first particle by the student to make it to travel, to make it to reach that 0.35 speed within 0.28 seconds. I hope this one was clear, right? Very easy maths. We only use the derivation for Newton's second law. Now, after this, it says that in another experiment, the first spark was pushed towards stationary with a speed of 0.41. Now, that is the initial velocity of the first particle before collision. And before collision, the second particle was at rest. And the paths of the two sparks before and after the collisions are shown. The paths are labeled as P1 and P2. Okay. Obviously, they're creating angles with the original direction, that is the horizontal component, and we have to distribute the force, like distribute the velocities. And masses are given, speed of Mach 1 after collision is given, but the speed of Mach 2 after collision is not given. So obviously, we're going to focus on the horizontal component over here again, because in the vertical component, what happens is they will eventually cancel each other out. Sorry, 1 minute. For example, over here, mass of Mach 1 was 0. This is 0.11 kg and this is 0.13 kg, right? And then again, before collision, you have the total momentum as 0.11 multiplied with 0.41, right? And nothing will be added because particle 2 does not have any velocity. And for the vertical components, you will have 0.11 multiplied with 0.28 multiplied with sine 49 degree, and then again this will be equivalent to 0.13 multiplied with velocity, which I do not know, I have to calculate that only, and this will be multiplied to sine 43 degree. Now I already know they are traveling in opposite directions, right? So they will cancel each other out. So I can also use a vertical component over here to find out the value for V, or I can use the horizontal component also. For the horizontal component, now you will have 0.11 multiplied with 0.28 multiplied with cos 49 degree, and this will be added with 0.13 multiplied with p cos 43 degree, right? Either one you use, eventually the particles or the value for velocity should be same. For example, if I'm going to use the vertical component, as you can see before collision, particle 1 and particle 2 does not have anything in the vertical plane, right? So that means before collision, the vertical plane was 0, and after collision, they will also has to be 0, like this one and this one. If you add them together, eventually their summation will also has to be 0 because before collision, the vertical plane was entirely 0 for the two particles. So in this case, if I want to resolve this maths using vertical planes, then sum of momentum before collision is equals to sum of momentum after collision. Sum of momentum before collision was 0. After collision is going to be 0.11, 0.28 sine 49 minus, this will be subtracted because they were traveling in different directions, 0.13 sine 43 with V. Right, so if you just take this to the left hand side, it will become positive 0.13, then sine 43, then V, and this is 0.11, 0.28, and then sine 49. And which means V is going to be 0.11, 0.28 sine 49 degree sine 43. 0.11, 0.28 sine 49, 0.13 sine 43. Yeah. Then you're going to get the final velocity of the particle 2 as 0.26. Okay, approximately 0.26 meters per second. And now again, if I use the horizontal component to find out the final velocity, I can also use that. For the horizontal component, resolving horizontally, okay? That is the same equation, total momentum before collision, and then again total momentum after collision, okay? So for the total momentum before collision, now only particle 1 has a velocity which was 0.41 exactly in the horizontal plane, and after collision they were both traveling in the same direction. Like you can see that both the components, horizontal component for the two particles, were in the same direction. And again, over here all of the particles are actually traveling towards right, so nothing will be negative or positive over here. So 0.11, 0.28 with cos 49, and this will be added with 0.13, 0. Sorry, I do not know the velocity over here. I tried, I'm looking for the velocity, so it is going to be cos 43 times velocity. Now from this part, if I just make velocity the subject, this is going to be 0.11, 0.41 minus 0.11, 0.28 cos 49 divided by 13 cos 43 degree. Yeah, you're going to get the same answer, 0.26 meters per second. Okay. Now you can choose any one of the methods, either horizontal component or vertical component. Which one is easier for you? You can choose either one of them and find out that unknown quantity. Please let me know if there is any problem from this working. Gopi, Bishama, Fatima, can you guys listen to me? Is there any problem from this part?
No, ma'am.
No, miss.
No, ma'am.
Okay, then we'll move on to the next part. For the next part now, we need to deduce whether this is an elastic or inelastic collision. Okay. For the elastic and inelastic collision, we're going to specifically focus on the initial and final velocity, right? So, total kinetic energy before collision should be equals to total kinetic energy after collision if the collision is elastic, right? So let's just calculate the total kinetic energy before collision, which is going to be half 0.11 times 0.41 whole square. I mean, the second particle does not have any velocity, so it won't have any kinetic energy too. So 0.5, 0.11 with 0.41 square, 0.5, 0.11, 0.4 square. This is going to be 9.25 into 10 to the power of negative 3. 9.25 10 to the power of negative 3 kg, so joules. And then again, total momentum. So total kinetic energy after collision is going to be half 0.11 with 0.28 whole square plus half 0.13 with 0.26 whole square. Now if we calculate them, this one turns out to be 8.71 into 10 to the power of negative 3 joules. So obviously we can understand that before collision, after collision, the energy is not conserved. So this is an inelastic collision, right? So we're going to write that sum of kinetic energy before collision is not equals to sum of kinetic energy after collision. Therefore, collision is not or collision is inelastic. And that is your final answer. And then again, explain the assumption made when applying the principle of conservation of momentum. When I was actually doing this calculation, what was my assumption? My assumption was that since they're giving you 2 marks for this, right? So there were two assumptions. The two assumptions were that I assumed the collision was elastic and there was no external forces acting on the particles during the collision, right? That was my assumption. That was the two assumptions I made to do that part A, right? A part 2, I think. I do this calculation. B part 1. Okay, the assumption for the calculations for B part 1 was I considered the collision to be elastic, even though I didn't calculate it that before this collision. And then again, there's another assumption was that all the forces, like there was no external forces that was exerted onto the particles during the collision. Right, so I'll just write down the assumptions that. Oh, wait, no. They're saying explain the assumption made when applying to this particle of conservation of momentum. We need to explain the assumption. The assumption was that the total, what was this? Sorry, the assumption was that energies, kinetic energies before and after collision was conserved. And we need to explain this, that why that was important, that why your kinetic energy before and after collision should be conserved. That is because if kinetic energy is conserved, then momentum is also conserved according to the equation. Kinetic energy is equals to, what was the derivation? Kinetic energy is equals to momentum square over twice m, right? That was the equation. Like even though they have a direct square proportional relationship, so eventually, if kinetic energy is conserved, momentum would also be conserved. But I'm talking about this equation. If you guys cannot remember, 1 over twice m p square. If you can resemble this is exactly in the form of ax square, which is a quadratic equation, right? This is also known as a square relationship, like kinetic energy is equal to the square of momentum. Right, so it doesn't matter if it is equal to the square of momentum, the square will only verify or will only create difference in the magnitude for energy and momentum. But at the end of the day, they are both directly proportional, right? So if in a collision, kinetic energy is conserved, in that case, momentum would also be conserved as they are directly proportional. Is there any question for this explanation?
Yes, how does this relate with collisions?
With this equations, right? Energy and momentum. This relates with overall energy and momentum, right? So if energy is conserved, then momentum is conserved, and only if momentum is conserved, we can use the equation total momentum before collision is equals to total momentum after collision, right? If they are equal, then that means what? That if you're going to add them, right? Like BC minus total momentum after collision, you're going to get zero, right? That's what indicates by the term conserved. That means no momentum will be lost during the collision. And that is only possible when energy is also conserved.
Okay, miss.
So according to kinetic energy, this equation, energy and momentum are directly proportional. So momentum is also conserved. And that is your explanation. This is what you're going to write in your answer. So 1 minute. This is your final answer, by the way. For Fatima Gopi, is there any problem for part C?
No, ma'am.
No, ma'am.
Okay. Now, if there is no problem, then this is it for your momentum. Now, we have finished linear momentum. We have finished angular momentum. I think from tomorrow we'll start with electric fields. But as I've already stated, we need to solve more worksheets also. This is your worksheet one we did in class, and there will be worksheet two that will be a homework, and you guys need to do that worksheet two within a week. Okay, so worksheet two, I'll upload that within tonight, and you guys have to complete that by next Wednesday or Thursday. Okay, we have to complete that by next Thursday, and give me the like upload your workings on the Google Classroom by next week Thursday, and that will be a worksheet two for momentum. And with this within this time, so you're not